Now I'm going to talk about the cardinality of sets. Don't worry, I'm not going to read all these slides to you, but it was easier to type some of this up than to write it out by hand. So there's times we want to know what the size of a set is. And typically the way we would measure that would be to use what's called the cardinality of a set. When the set S is finite, that is, it has a finite number of elements, then its cardinality is just the number of elements in the set. And there are different ways to write cardinality, but this is one of the more common ones, to use the vertical bars like absolute value. So if I look at set S here that contains the elements A, B, C, and D, we can see that there's 4 letters here, and therefore I would say the cardinality is 4. T here happens to be the empty set, so if I look inside the brackets, I don't see anything, and therefore the cardinality of the empty set is 0. When we're discussing finite sets, the size of the set matches up with what your intuition probably is. That is, I can look at this and say, well, how many things are in this set? 1, 2, 3, 4. Okay, that's what the cardinality is. It turns out, though, that when we're talking about the cardinality of an infinite set, it's not necessarily what we might expect it to be. And in fact, we can have 2 sets that both have an infinite number of elements whose cardinality is not the same. Before we look at that, though, let's talk about another way to think about cardinality. And that is that 2 sets, A and B, have the same cardinality when there's a bijection from A to B. And we'd write it like this: the cardinality of A is equal to cardinality of B. This is true when we're talking about finite sets or infinite sets. All right? If you haven't seen my video talking about sets in terms of or functions, in terms of set theory, in which I discuss the definitions of bijective functions, surjective functions, and injective functions, you may wish to go back and look at that. But this sort of sums up what we're talking about here. When we are talking about infinite sets, though, we can divide those into 2 subsets. And those 2 subsets are those infinite sets that we call countably infinite and those that we say are uncountable. So a set S is countably infinite if there's a bijection from the set of positive integers to S, and in that case we would say they both have the same cardinality. Recall that a bijection means that the function is both 1-to-1 and onto. So if we have a 1-to-1 function from set A to set B that is not also onto, then we don't have a bijective function. In that case, though, we would say the cardinality of A is less than the cardinality of B. Notice here I'm not putting an actual number to it, because if we're saying A has an infinite number of elements and B has an infinite number of elements, I can't really put an actual number to this. I just know that this cardinality is smaller than this cardinality. Now the set of positive integers happens to be countably infinite. So if I were to have a set B whose cardinality was larger than the cardinality of the set of positive integers, then we would say that set B is an uncountable set. And that happens to be the case for the set of real numbers. Its cardinality is larger than the cardinality of the positive integers. Let's revisit, though, the idea of the bijection from the set of positive integers to some other set. So this is true. The set of even positive integers is a subset of the set of positive integers, which itself is a subset of the set of all integers, which we normally say is just the set of integers. So what we're talking about here, the set of even positive integers, that's 2, 4, 6, The set of positive integers, that's 1, 2, 3, 4, And the set of all integers would be ... because we have negative numbers going in the negative infinity direction. -2, -1, 0, 1, 2, ... This is true. This is a subset of this. This is a subset of this, which means this is also a subset of this. And you're probably looking at it thinking, wow, this then must be smaller than this, which is smaller than this. But in terms of cardinality, that's not necessarily the case. All right. So remember what we said. If we can find a bijection from the set of positive integers to some other set, then they have the same cardinality. And what that means is coming up with a way of mapping every one of these numbers to the numbers in the other set, or the elements of the number set. I guess it wouldn't necessarily have to be numbers. All right. So let's say here, we'll call this set A, set B, and set C, just to make it easy to distinguish between what I'm talking about. So A will be the set of positive integers, B will be the set of even positive integers, and C will be the set of all integers. And really, this is, let's just do this. This is Z, because that's the standard way of talking about it. So if I were to have that A was an element of set A, right? So we'd have 1, 2, 3, 4, 5, dot, dot, dot. What if I were to write down 2A? Well, 2A would be 2, 4, I'm going to put some lines here, keep them straight, 6, 8, 10, dot, dot, dot. Well, this right here is set B. I just found a mapping, so that way, for every integer in the set of positive integers, I can show how to get to one of the elements of set B. And I can go back the other way. We could take one half of these numbers and come back this way. So therefore, I have the bijection, and that means that the cardinality of A is equal to cardinality B, and the set of positive integers happens to be countably infinite, so that means that B is countably infinite. All right? It's probably messing with your head. You're looking at this saying, yeah, but you skipped every one of these numbers, so how could this be the same as this? It goes back to the definition about the bijection. Okay? If this is a set and this is a set, I can get to every one of these elements from a single value over here. And that's where the bijection comes in. What about set Z? Okay, so once again, if I have little a is an element of set A, and if A is even, I'm going to produce A divided by 2, and if A is odd, I'm going to produce the negative of A minus 1 divided by 2. So when A is 1, that's odd, so I have minus 1 minus 1 over 2, which is minus 0, which is really just 0. For 2, that's even, so I have 2 divided by 2 is 1. 3, this would be now minus 3 minus 1 divided by 2 is equal to negative 1. 4, that's 4 divided by 2 is 2. 5 minus 5 minus 1 divided by 2. So it's minus 2. So what am I producing here? Well, I don't have to write the integers in order to represent the set. I just need to be able to represent everything there. So what I'm producing here is this set. 0, positive 1, negative 1, 2, negative 2, and then you can see how I'm just continuing. So this right here is the set of all integers, which means the set of all integers is countably infinite. Let that sink in for a minute because it may be hurting your head. But like I said, once again, it goes back to the definition of the bijection between the set of positive numbers and the set that we're looking at. Okay? So now you still may be thinking, my gut still tells me that, for example, the set of even positive integers has to have fewer elements than the set of all positive integers, right? Since I didn't write down the odd ones. Well, there is a concept in number theory that's closer to what your intuition would be. And that idea is called the natural density or the asymptotic density, right? So you can find different definitions online, and sometimes I also talk about the lower asymptotic asymptotic density or the upper asymptotic density. But this definition, which I got from here, is talking about, see the vertical bars here, A of x will be the cardinality of the set where if S is a sequence of positive integers and we choose those elements in the range of 1 to x, okay, and take its size, the cardinality, then if I were to take the ratio of that to x as x approaches infinity, this will give me an idea of the density of the set we're looking at. So what does that mean? Well, let's say, for example, that we say S is the set of even positive integers. All right? Well, then if I were, say, for example, let x equal 5. Well, then if we look in the range of if n is an element of S, and we're looking in the range of n is less than or is in the range, of 1 to 5, then what we're producing here is this subset of S. That would be 2 and 4, right? Because the set of even integers would be 2, 4, 6, 8, 10, forever. So what happens if I take the cardinality of this? Cardinality of that is 2. And if I take the ratio of this, so what we just produced is AX to X would be 2/5. Okay? So now, if we use the formula that the density of S is the limit as X approaches infinity of this ratio, that is, if we were to keep adding elements, if I add a third element and a fourth element, whatever, look at this ratio, what we eventually will get here, in this case, will be 1/2. And that's more in line with my intuition that somehow I have half as many even positive integers as I do total positive integers. But that's in terms of this definition, that is the natural density of the set of numbers, not the cardinality. They each have their place, and there's lots of different ways you can define sizes, but this is one way of doing it, which is closer to what you might think, that there's half as many of these even positive integers as total positive integers. But the cardinality says that, in terms of cardinality, that the cardinality of the set of even positive integers is equal to the cardinality of the set of all positive integers. Right? They're not the same, and they're not necessarily used in the same places, but this might be closer to what you're thinking. But if you're still struggling with this idea, and I did for a long time, it really helped me once somebody pointed out that it really ultimately came down to looking at that definition about the bijection. And if you think of that way, instead of trying to stick to your normal idea of size, it might be easier to stomach this idea.